Kia ora. This STAT193 video is going to take you through a problem using the Chi-square test and show you how to use your graphics calculator. This is the context that we're going to look at. This problem comes from the 2011 Trimester 1 exam. The data below are from a study to determine which type of psychotherapy works best for panic disorder. There are 4 treatments involved. We can see those here: cognitive therapy, relaxation therapy, drug treatment, and the control group. At the end of the course of treatment, the following results were self-reported by the 320 patients who took part in the study. We can recognise that this requires a chi-square test because the data that we've got is in a contingency table. In this contingency table, we've got 2 categorical variables. So we've got the type of treatment and the degree of relief from panic attacks. Okay, so the first step that we need to do is we need to write out our hypotheses. Our null hypothesis is that our 2 categorical variables, degree of relief and type of therapy, are not associated. Now, you might have come across different wording for this, such as that the 2 variables are not correlated or that they're independent. It doesn't matter which choice of words you use, so long as the null hypothesis is getting across the idea that there isn't a relationship between the 2 categorical variables. Our alternative hypothesis is that those 2 categorical variables are associated. Step 2, we need to calculate the expected frequencies and the test statistics. Okay, so for the expected frequencies, we're going to fill in a table that looks quite similar. I've got the totals in there already because they're not going to change from what we've got above. But the expected frequencies we're going to fill in here are the frequencies we'd get if our null hypothesis was correct. So going into STAT in the main menu, we go into Test, F3 for Chi-square. We've got a 2-way table, and we're going to put our observed frequencies into matrix A. So we go F2 to go into the matrix, and it's matrix A that we're interested in. We need to go F3 to tell it the dimensions, and we need to enter values for M and N. So M is the number of rows, so we've got 4 rows here, so we can enter in 4. And N is the number of columns, so we've got 3 different categories for the degree of relief. So we've got 3 columns, and execute. That brings us to a matrix where we can now enter these observed values. And it's worth just taking a few seconds just to check that the data's all been entered correctly so that you don't make unnecessary mistakes and lose marks in assessments. Okay, once you're happy with that, exit out again, and we're now back to the chi-square test, and we can execute that, and it's calculated our chi-square test statistic, our p-value, and our degrees of freedom. But we can't use these values yet. We first need to go into our matrix, so F6, go down to matrix B, because this is where our expected frequencies are. And we can see the expected frequencies and now fill in this table. Okay, it's really important when you fill out this table that the expected frequencies are not rounded to whole numbers, so you want to leave 1 or 2 decimal places. What we want to look at this table before we use the test statistics is we need to assess and check that at least 80% of those cells have expected values of 5 or more. If we had too many small values, we would need to amalgamate some of the cells. You can see your lecture notes for details of how to do this. Okay, so because all our numbers are nice and high, we've got no problems there at all. So we want to go on and actually look at our test statistics. So we can exit out of this and again come back to that screen. So we can now report our chi-squared value of 18.4677, our p-value of 0.0051637, and our degrees of freedom of 6. So you can see we can get our degrees of freedom from a graphics calculator, but we could also calculate it by looking at our table, seeing that we had 4 rows and 3 columns. We take 1 off each of those numbers to give us 3 times 2, which is the 6 degrees of freedom that we see. Okay, we've got that. We're going to go on now and calculate the critical value and the rejection region. So to do this, we need to exit out, come to distributions. It's a chi distribution. Inverse chi will give us the critical value. We check that data is on variable. The area that we enter here is our alpha value, which is entered already in this case as 0.01, which is what we want. And our degrees of freedom, it'll remember this from the chi-square test you just carried out, so you don't have to enter that in, but you can just do a quick check to make sure it's what you thought. Execute that. And we get an inverse chi of 16.81. Okay, so we can 16.812 to 3 decimal places. Okay, we've got that critical value. Now let's sketch our graph of our chi-square distribution with 6 degrees of freedom. Mark on the area which corresponds to our alpha equals 0.01. Put in our critical value here. So this marks the start of our rejection region. And we can now take our test statistic for our chi-squared and put that on as well. And we can see here that chi-squared, the test statistic, is within the rejection region. Let's bring these 3 steps together now, side by side, and we can then draw our conclusions. So our first step was to set out our hypotheses, with our null hypothesis being that the 2 categorical variables were not associated. In step 2, we calculated and checked our expected frequencies and calculated our test statistics, and we did this using our graphics calculator. In step 3, we calculated our critical value, which marked the start of our rejection region, and we could see that our test statistic lay within that rejection region. In step 4, we draw our conclusion. So we're going to reject the null hypothesis at the alpha equals 1% level. So we do have evidence for an association between our 2 variables. Our evidence for this was that our test statistic was within the rejection region. So 18.4667 was greater than 16.812. The other piece of evidence was that the p-value was less than alpha. So 0.005167 was less than our alpha value of 0.01. Both of these pieces of evidence are consistent, and they always will be, and we can use either to make our decision.